Have you ever wondered what the blueprints of the universe look like? Well, today we're going on a journey into this hidden world called abstract algebra. And don't worry, this isn't about solving for x in high school. This is about discovering the secret rules, the fundamental patterns that govern everything from a simple clock to the very fabric of reality. So let's jump right in.
So here's our game plan. First, we're going to completely rethink what math even is. Then, we'll build a powerful idea from the ground up, starting with a simple playground of objects. We'll add some rules for how to play, and then we'll assemble the whole thing into this really elegant, perfect structure called a group. And to wrap it all up, we'll see how this amazing concept shows up in something you use every single day, a clock.
All right, first things first. Let's challenge some of those old ideas we have about mathematics.
I want you to really think about this for a second. What if we just forget about crunching numbers and solving equations? What if instead math is actually about being a detective? It's about finding the deep underlying patterns and rules that make things work. I mean, anything. Abstract algebra is the language that lets us talk about the very essence of a system, the logic that holds it all together.
Okay, so if we're going to build these incredible structures, we need to start with the most basic building block. And in abstract algebra, our foundation, you can think of it as our playground, is the idea of a set.
Now, that's the official definition, straight from the textbook. A well-defined collection or class of objects. It sounds a little formal, right? But that key phrase, well-defined, is actually super simple. It just means you need a clear yes or no rule for deciding if something belongs in your collection or not.
And these objects? They can be literally anything you can imagine. Your set could be the numbers 2, 4, and 6. It could be the countries India and Burma. It could even be a collection of all the rivers in India. See? A set is just a box of stuff. That's it. That's our playground.
So, we have our playground, the set. But, a playground with a bunch of stuff just sitting there is, well, it's pretty boring. You can't do anything. So we need to add some action. And in the world of math, we call that action an operation.
This sounds way more complicated than it is, I promise. A binary operation is just a simple rule, like addition or multiplication, that tells you how to combine any two things from your set to get a result. But, and this is a big but, there is one absolutely critical catch.
The operation has to be closed. Think of it like this. Our playground now has a fence around it. Closure means that no matter what two things you pick from inside the playground, when you combine them using your rule, the answer always lands back inside the fence. You can never, ever escape the playground.
This makes it perfectly clear. On the left, imagine your playground is the set of all even numbers, and your rule is addition. You're totally closed. You take an even, add another even, and you always get an even. You're always inside the fence. But look at the right. If your playground is the set of odd numbers, well, you've got a problem. You add an odd and another odd and you get an even number. Uh-oh, you've just jumped the fence and landed outside the playground. And for the kinds of perfect structures we want to build, that's a deal breaker.
Okay, this is where it all starts to come together. We've got our playground, a set, and we've got a rule that keeps us safely inside the fence, a closed binary operation. Now, by adding just a few more simple rules, we get to build one of the most beautiful and important structures in all of mathematics. It's called a group.
These are the 4 rules, the blueprint for a group. Number 1, closure. We already know that one, the fence. Number 2 is associativity. This just means the parentheses don't matter. It doesn't matter how you group things, the answer is the same. Number 3, you have to have an identity element. This is like a home base. It's one special element that when you combine it with anything else, it doesn't change that thing. For addition, that's 0. For multiplication, it's 1. And finally, number 4, every element needs an inverse. This means every single move you make is reversible. For anything in your set, there's a buddy that brings you right back to home base.
So let's put this to the test. Let's take the set of all integers, positive and negative whole numbers, with addition. Is it a group? Well, it's closed, the identity is 0, and for every number a, the inverse is just negative a. So, yes, it checks all 4 boxes. It's a group. But now what about the natural numbers, just the positive counting numbers with addition? Well, it's closed, sure. But is there an identity? Nope, 0 isn't in that set. Are there inverses? Nope, no negative numbers. It fails on 2 of the 4 rules. And here's the key, it has to be all 4, no exceptions.
Okay, I know this has all been a little bit abstract, so let's bring it back down to earth and look at a really cool, perfectly self-contained example of a group that you probably use without even realizing it. We're going to play with something called modular arithmetic. Just imagine a clock, but instead of 12 hours, it only has 6, and they're numbered 0, 1, 2, 3, 4, and 5. That's our entire set, our entire playground, and our action is going to be addition.
The rule is actually really simple. You just add two numbers like you normally would, and then you just find the remainder after dividing by 6. So, for instance, what's 4 plus 3? It's 7, right? But on our little 6-hour clock, you go all the way around once, and you have 1 left over. So in this world, 4 plus 3 equals 1. It's really just clock math.
And check this out. This table shows every possible addition you can do on our 6-hour clock. And just look at it. Every single answer in that grid is a number from our original set, 0 through 5. You can't escape. It is a perfect, tiny, self-contained universe. The fence is strong.
So let's run our 4-point check. Is it closed? Oh yeah, the table proves it. Is it associative? Yep, it is. Is there an identity, a home base? You bet it's the number 0. Adding 0 changes nothing. And finally, can every move be reversed? Is there an inverse for everything? Yes, the inverse of 1 is 5 because 1 plus 5 is 6, which on our clock is 0. The inverse of 2 is 4, and the inverse of 3 is 3. It passes with flying colors. This is a perfect mathematical group.
Now, why is this so important? This isn't just some cute math trick. It turns out that this structure, the group, is the fundamental mathematical language of symmetry. Think about a hexagon. The 6 rotations you can make that leave it looking exactly the same, that forms a group that behaves exactly like our 6-hour clock. This same elegant structure is used to describe the behavior of subatomic particles in quantum physics and to build the uncrackable codes that protect our information online. It's a blueprint that shows up everywhere.
So just by starting with a simple idea of a playground and adding 4 simple rules, we uncovered this incredibly deep structure that helps us describe the universe. And that really makes you wonder, doesn't it? What other elegant hidden patterns are out there just waiting for us to find them?